You've heard it so much.
Well, it depends. Are you talking like A to B?
Yeah, what did you keep doing in the past?
Well, are we talking integrals or are we talking derivatives? Because it could be, there's always going to be a point tangent between point A and B on the line that's going to equal 0 just so long as...
I know, but when it comes to differentiation, that's so clunky. It's so much nicer with differentiation, plant your feet at A and move certain number of units to the right instead of moving to another Z. So Eric, I'm being goofy. I was hoping you'd yell at me saying, yeah, we're just gonna get a regular partition of the interval from A to B. You guys done this so many times.
It's a very
And-
fancy word.
What is a fancy word?
Partition.
Yeah, that's something that I would think of that more of as a computer science word than anything else.
Would you really?
Yeah.
Because I think of the word partition in mathematics, always just taking something and subdividing the parts, even sets. Actually, that is a set of real numbers from A to B. And when I use that word, that adjective regular, it simply means all the subdivisions have the same length. Like how somebody talks outside the math classroom, they've got a regular pentagon, meaning all sides have the same length. And I will label appropriately x1, x2, the heck with it. Let's talk about the arbitrary subinterval. Even down to maybe the last subinterval. But this time, you guys, instead of taking area under the curve, let me do something slightly different. Let me go ahead and talk about what's going on in the subinterval. Look at the endpoints. And let me talk about the line segment connecting those two purple points. I do not think the length of that line segment is the same as the length of the curve over that subinterval. But I do think as n increase that bound, that is to say the number of subintervals I have, as that number of subintervals increases with that bound, I do think the length of that purple line segment is getting closer and closer to the length of the curve. So maybe with this limiting process, I will be able to talk about the length of the curve over the subinterval. And here's how I'm going to do it. I am going to connect the purple point with the purple point with a horizontal green movement and a vertical blue movement. You guys have seen this before back in Math 30 when it came to the
Derivatives? No. Differentiation.
differentials.
Differential.
Differentials. You defined them the same way, didn't you? It was a nifty little right triangle. I maintain a small change along the curve, which actually is not true. Small change along the purple line segment, which approximates the change of the curve. Could be interpreted in terms of my horizontal and my vertical deviations. Because I do think if you treat dx and dy as differentials, this is a right triangle. I maintain the square of ds is the sum of the squares of dx and dy. That being the case, I think ds itself could be interpreted as the square root of the sum of the squares of y is equal to sine equals sine. You guys seen this back in Math 31 as well with arcline, haven't you? So I also maintain that if I want to, I can think of ds as the square root of 1 plus the derivative for y with respect to x twice. Oh, shoot, what did I just do? I just pulled out a dx, didn't I?
Yeah.
I don't have to. I could just as easily pull out a dy. In other words, like back in Math 31, I have two choices for how I interpret that differential for s. Now when I take the limit of the Riemann sum, I come up with the arc length. You guys have already done this. Can I just maintain in three-dimensional space? I can play a very similar game. Because I think in free space, I can also generate a differential in the same darn fashion. Nothing changes. So do you guys think I can stall for a minute? Actually, if you open up any calculus text, you are not going to find a section on arc length. It's got a lot of examples. Because most examples I can create off the top of my head, actually they're very limited. It's really difficult to make up an example of arc length when you want an integral that's integrable, only because it's squaring business. So can I cheat? I know I made up some examples for last week. So if I were to do something like, I don't know, how about this? So if you guys, you really want to impress somebody at the next party you go to, just talk about the circumference of a circle. Just do it in a more elegant fashion. How can I describe a circle with a vector value function?
Well, you could write a vector from the center out to the edge and then rotate it
True,
around.
and so what will those components look like?
Radius times your sine.
Radius times, you want sine? The next one will be,
R cosine t, right? Something like that.
or vice versa, if the order is not important. I mean, that's a vector representation of of the circle, isn't it? And for you to come up with arc length,
Is that in free space or free space?
you know, I just meant this to be two-dimensional space, only because I was talking about the circumference of a circle. I'm so sorry. Excuse me.
So what would be the third component to make that a sphere?
Well, if you want a sphere, isn't that going to look like this?
X is our sine t, y is our cosine t.
And if that's going to be a sphere, I can't really use one parameter like this to talk about a surface. So I'm going to have two parameters for the equation of a sphere. And I'll do this once I start talking about equations in two parameters.
Deal with that later. then.
Yeah, we'll deal with it later. We're going to get to it though.
Now, what about a circle in free space?
Well, then you just don't put the z component in there.
No, because that would be, then that would extend one,
Oh, you mean one that's been rotated? Is it? Okay.
Linda, it depends on how you want to do it. If you just want a circle in three space hovering, say for example, above the xy coordinate plane, it's a piece of cake. You just add a z component, that's just a constant.
okay.
If you want slanted, that would be more complex, because now you got to worry about the z component changing. I mean, you could do it, I just don't think it's quite as easy.
So you would have to have the third vector, okay, because you only.
You would have to
only
have
have
a
an
third
x and y component, so this is only two space automatically.
I agree.
Okay.
And everybody, if I were to use my formula from back in Math 31, I see the area can be computed by looking at the integral from a to b of nothing more than the square root of 1 plus dy dx.
Area?
That's the arc length, right? Why are you stalling?
You said area.
You said area.
Did I really? My apologies. I'll slow
Yeah.
down. Arc length. You guys happy? Why are you stalling?
Well, it's not a vector value.
Thank you. I guess this isn't really meant to give me the length of an arc. If I've got a vector value function, I got to do it all over again. Can you come back over here? Instead of pulling out a dx or a dy, let's do something different. Let me pull out a dt. And I think my differential for s could be interpreted this way: the sum of the squares of the derivatives with respect to t for x and for y. But like I said, I better pull out a dt. In terms of differentials, it's just as legal as what you guys did back in Math 31, down here and down here. And so I guess to actually compute the length of this curve, I'm going to have to integrate the square root of my dx dt squared. I said my dx dt squared.
R squared, sine squared.
R squared cosine squared t plus,
Order doesn't matter, but yeah.
Minus r squared?
you're right, negative r sine of t quantity squared, but when I square it, I get rid of the negative sign. I'm integrating with respect to t, but tell me what my bounds are. 0 to 2 pi. Because t is really representing an angle.
Oh, so it would be more like pulling out a d theta, okay.
And you know what? If you want to call it d theta, go for it. I'm going to do the same thing in a few minutes. And I maintain, oh, you guys, life's such a piece of cake, isn't it? Isn't it just simply an r squared? I don't need the square root symbol.
Oh yeah, because you can pull that out of cosine squared plus sine squared as well, okay.
Using Pythagorean identity. Oh, shoot, look at that. That is the area of a circle.
Just
Area.
really
That
quickly,
is a circumference of a circle.
You just pulled out those bounds because that's just the range of cosine and sine? I mean,
Well, I just recognize within the circle, I can span the entire circle with
Yeah.
full rotation. If you interpret the t as an angle.
Okay.
Which makes me envision-
so oftentimes we have to create the bounds ourselves, they wouldn't be given to us?
Oh,
Or-
yeah, absolutely.
Okay,
Yeah, if I were to ask you a question like this, I expect you to come up with those bounds on your own.
okay.
Oh no, shoot, we're still stuck in two space. What if I had a vector value function, an r bar t, that look like this. 3 components. The first component is some function for x in terms of t. Second component is some function for y in terms of t. Third component is for z's. Then I think the length of my arc, likewise, is going to be computed by looking at the integral from a to b of the square root, the sum of the squares of the derivatives with respect to t for x, y, and z. Just like I generated the Pythagorean, oh, I misspoke, didn't I? Just like I generated the distance formula in 3-space, probably the very first day of class, exactly the same idea. And we can use it.
Is there a dt in the L? Oh, no, no. So you're not undistributing the data, you're not pulling it out?
I am, my
Oh,
apologies.
okay,
Of course
sorry.
I am.
So if you pulled it out, wouldn't you get rid of it in the denominators on the inside? Or in the notation on
No,
the
it's-
inside?
it's-
Okay,
Derivative
well,
x-
double check me, see if I made a mistake.
Okay.
If you treat this as a differential,
Okay,
you bring it aside the square root, it becomes a dt squared.
okay.
Cancels here, cancels here, cancels here, and I get what I initially started with in 3 space.
Okay.
Alright.
So the algebra works. Oh, you guys, I have to come up with an example. How about something like this? E to the t plus,
Why, you want to just throw something out?
no, something interesting.
1.
E to the
One is a very interesting number.
Negative t, because that reminds you of
The hyperbolic something, or cosine
Hyperbolic.
of, or, no, that's a sine, that's a,
What? Is it?
huh?
Cosine.
Hyperbolic
I don't
cosine?
recognize
Alright.
it.
Oh, you guys are killing me. How about 3 plus 2t? Oh, that's not in free space, darn it. Oh, well.
Wait,
It's still too good to pass up. So I think for you and I to compute the length of the arc over the interval from 0 to 1. Hey, you guys, I'll slow down. Here's where the work is. I think in the Radicand's position, I simply need the square of this first component's derivative. What would that be?
cosine hyperbolic squared?
Well, there's no 2 in the bottom, so.
Oh, okay, so then,
Nice thought.
e to the t minus e to the negative t?
Yeah, I could have multiplied by 2, you're right. And that's fine. You rewrite it in terms of hyperbolic sines and cosines. It'll work.
Okay.
I think this might be a little easier. Because I think I need to add to this
The square,
just a positive 4.
yeah.
What? Oh.
And that's going to give me some 0 to 1 the square root of, let's expand. Isn't this just going to be this in green?
Huh?
Yeah.
Okay.
There
Okay.
we go.
What exactly is it that you wrote right there? You know, I'm still trapped on your handwriting, so, is that?
Over the interval?
Oh, okay.
It's not a square symbol. Did I forget anything?
Where did the 4 come from?
I differentiated this, got a 2, and squared it. It was really my dy dt squared. Come on, you guys, are you happy with this? Oh, I forgot the plus 4 in black. However, if I now combine my terms in Radicand's position, you guys, doesn't that give me this? From 0 to 1 in blue.
Okay, what
What
happened? What happened there?
I made a mistake. Where's the mistake?
Other
It
than
says
the
plus 2. Why am I using all this color?
Oh. Oh, you can just add the four. You just combine like
Yeah.
terms. Okay.
Yeah, I know, but is that significant? Hugely, hugely. What you saw in green was a trinomial equivalent to a perfect binomial square. What you see in blue is the same thing as what you saw in green, a sign change in the second term of the trinomial. So I think for free, you and I should be rewriting this as the integral from 0 to 1. The square root of,
Square root of e to the 2t.
e to the
e to the t.
e to the t
plus
plus.
e to the negative t squared. All of that squared. Square
Oh,
root of that.
very nice. So now I think the squaring and the square rooting undo each other, and I'm merely left with the integral from 0 to 1 of e to the t plus e to the negative t. Isn't life a piece of cake? But that's merely gonna give me e to the t minus e to the negative t evaluated from 0 to 1. But cheapers, you guys, here too for free, isn't that merely gonna give me an e minus 1 over e? Or would you prefer an e squared minus 1 over e? Man, your quietness is killing me again.
No, no.
Isn't it easier just to switch over to hyperbolic? Because then you just have to worry about certain coefficients in there.
Probably not, because you have the,
You know what? For the hyperbolics, you're right, it does
this right
work
here-
nicely, but the one problem you have with hyperbolics is you have to remember this, there's no board space. You have to remember hyperbolic cosine, square root of t plus hyperbolic sine square root of t is equal to 1.
No, isn't it minus?
Yeah, I'm wrong, and that's where I think it's tricky. You have to remember that it's subtraction, not addition. That's why I probably would have avoided it.
what? So isn't it sine hyperbolic t? Not just sine square root of t? Because you put a hyperbolic
Oh,
minus
sorry, I didn't notice I didn't put the h in, my apologies.
okay,
Yeah, you know I'm talking about hyperbolics.
okay.
Are these really the same thing? They really the same thing?
No.
I don't think so.
You allow t to be complex. Turns out they overlap beautifully. Those of you who are taking honors from Math 33 this semester, I'll make sure you prove that. Sorry, I'll come back. I don't like my example. I said I wanted to jump into 3 space, but I'm not going to struggle beating that clock, making up an example out of thin air. So if you guys don't mind, how about this? R bar of t being equal to t, 1 over root t squared. How about 1/3 t cubed? Yikes. Here too, if I'm trying to find the length of the arc, I never gave you numbers, did I? Eric, I'm thinking of you.
Over what?
Oh, that's not nice enough.
That was probably the nicest you've ever written.
Because you shamed me into it. And so now when I compute the length of the arc, here too, you guys, from 0 to 1, underneath Radican's position is where the work is. I'll slow down. I think dx dt is just 1.
Yes.
And a square to get the same thing. I think my dy dt is a root 2 times t. But when I square it, I get 2t squared.
How did that happen?
I think my dz dt is just t squared, but when I square it, I get this. And I'm going to integrate with respect to t. Now, question. Can you guys integrate this thing? What kind of trig sub would you use?
Just factor.
Yeah, how about none of them? Let's just be really simplistic with our math D skills again. I think it's a trinomial equivalent to a perfect binomial square. Do you guys agree?
Yeah. So that's what all these examples are. It's these. Oh.
And so I guess I'm merely left with something this simplistic. Ah, shoot, you guys, isn't life a piece of cake? Does that give me a 1/3 t cubed plus t evaluated from here to here? Or shall we just say a 4/3? You guys okay with that so far?
Yep.
So can we expect trig sets in the future for these kind of questions? Have a square root instead of something that doesn't cancel.
Can you just be honest? I don't ever remember creating an example like that would involve them, unless it's just something as simple as Pythagorean theorem,
Yeah.
or Pythagorean identity like I have earlier. Guys, I'm really gonna be honest, it's so hard for me to write sophisticated questions with hard things.
What if you had like sine of t and cosine of t, and then you'd have like a sine square, or a cosine squared of t?
And that's what I was saying, Pythagorean identity, really, really easy for me to do that.
So with, if you wanted to ever solve an arc length problem that didn't involve the square root of disappearance, in terms of solving using
I will be able to comprise some examples, so you can make quick and easy. So, just because of all the square root doesn't mean I can't back it.
Yeah, but a lot, I mean, if you wanted to find the arc length of something that just you couldn't do it with this, would you have to create a series representation and?
Not necessarily. I mean, another approximation technique you have under your belt is just using Simpson's rule.
What?
Simpson's rule would be another alternative.
Oh, okay.
So it doesn't have to be power series. You know, something like this really wouldn't be a good candidate for power series, only because it's already fallen on me. Oh, you guys, I have a few minutes. I can play. You guys ever see a function like that?
Function of theta.
Where? Whoops.
Geometry.
Yeah, all over the place. Polar representation of a curve. So you guys actually integrated differentiated polar lines,
Kinda.
kind of. But R can be interpreted as a function of theta. And so if I had a vector valued function, R bar, evaluated parameter theta, maybe this one right here, my x as a function in theta, comma, my y as a function in theta. Actually, parametrically speaking, I guess x could be interpreted as nothing more than my r times, well, cosine of theta, comma, r times sine of theta, where it's understood that r actually is a function in theta. Theta is my parameter. So if I were to differentiate x with respect to theta, wouldn't I have to use the product rule? Since r is understood to be a function of theta, I think I get the derivative of r. Is that
Cosine theta.
What is that? I'm gonna be dx.
dx d theta?
Oh.
And I'll multiply it by. You guys are killing me.
The cosine of theta. And then the next one is gonna be add r derivative of cosine is negative sine.
I like it. Oh, you guys are on a roll. I said you're on a roll.
Plus R cosine.
Oh, but wait a minute. That means my arc length formula becomes this. Let's see, the integral from alpha to beta of the square root of the squares of dx d theta and dy d theta. Or shall I say, that gives me the integral from alpha to beta of the square root of, oh shoot, you guys, here we go. I need a lot of room. So you ready? Well, if I square dx d theta, doesn't that give me an r prime squared cosine squared of theta minus 2r r prime sine theta cosine theta plus r squared sine squared theta. Those three terms I have on the input are the result of nothing more than squaring dx d theta. Oh shoot, more math D business. I'm running out of room. I'll come down here. I better add my dy d theta, but jeepers, using the same logic. It's not going to be r prime squared. Sine squared of theta plus 2r times r prime times the sine of theta times the cosine of theta plus r squared cosine theta squared. You guys, do you think I could just stop? It's getting too sloppy, isn't it? It's getting too sloppy. No, I don't think that's getting too sloppy at all. You guys check this out. In red. Not only are these two terms like terms, they're additive versus cancellation. Not only that, but you take a peek at these two circled blue terms, this one and this one.
You got a Pythagorean identity that you can use.
Yeah, you factor out
If you
r
factor out
prime
an r
squared,
prime
you're
squared.
gonna get cosine squared plus sine squared, which is just,
1.
oh, how beautiful. I just got the integral from alpha to beta of an r prime squared. Did I miss it?
Yeah.
Yeah, I think I missed a lot. Look what the stuff in green is. In green, we've got an r squared sine squared. Oh shoot, over here, r squared cosine squared. Here too, pull out an r squared, what's left over is
1.
just 1. I guess if I've got a curve described in terms of polar representation, I've got a whole new nifty formula I can use to compute a certain plane. Do you mind if I don't give you any homework on that one? I'd rather just give you an example first. Speaking of examples, let me come back. I'm sorry I'm so slow. Can you guys dive into 11.7? Lessons. Take a peek at these. 7 to 11 on it. 19. 327 on it. Thirty-one, 33, 35, 37, 39.
So 31 through 39 odd.
Yes, you could hide that. How about 43? I like 49. In addition to that, in section 1.8,
Is that, what's 43 underscore 49 mean?
it's 43, comma 49.
Okay.
Can you guys take a peek at 11.8? Just not that much in here. Look at 7 through 17 on. Oh, you know what? I hate even numbers, you guys, but this one's so nice. You've got to take a peek